Hello everyone. The title of this video is Comparing Smooth and Continuous Graphs. So each example I'm going to be taking for this video is directly from a free online textbook at openstax.org. I'm in their Algebra and Trigonometry text, section 5.2, called Power Functions and Polynomial Functions, and I'm under the heading Comparing Smooth and Continuous Graphs. Alright, so each example I'm doing in this video is either going to be an example from the reading or one of the try it problems from the reading or one of the exercises at the end of the section that's related to this particular objective. Alright, so before I get into the first example I want to do the try it problem number 7 from this section. I want to talk about what it means for a graph to be smooth and for a graph to be continuous. Right. What does continuous mean? Smooth mean? Right. So continuous graphs they have no breaks. There are no breaks or holes in the graph. Right. So some examples. Let's do this in a different color. So a graph like this would be continuous. Right. There's no, I didn't have, basically you don't lift your pencil or pen. A graph like this with all these sharp turns in it. I didn't lift my pencil the entire time. This would be continuous as well. Now on the other hand, a graph like this, say where it goes for a bit, then there's a hole, and then makes a bit of a jump, and then continues on. See, I had to lift my pencil to draw the rest of it. Right? There's a jump, there's a break in the graph. So a graph like this would be, not continuous or discontinuous at this value, at this point here. I'll just say it's not continuous. And a graph like this where it looks like continuous but it's missing one point. All right, this is representing a hole in the graph, a missing point. All right, and here, this right here is a break in the graph. This is also considered not a continuous function, not a non-continuous graph. All right, so again, continuous graphs have no breaks, no holes. You draw it without lifting your pencil, right, or your pen, whatever you're drawing with your marker. Right. If you have to lift your pencil, or if you have to make a break or a hole in the graph, then it's not continuous. I hope that is clear. Now, smooth graphs smooth graphs have no sharp corners, no sudden turns, no sharp corners. Another way to say this is that their turning points, and I've brought up turning points in a previous video. Remember, a turning point is where a function or a graph goes from increasing to decreasing, from going up to going down. Turning points occur at, rounded corners. So like this or like this, but no sharp turns. So basically no pointy places like that, or like this where it's sharp. These would still be turning points, because you're going from increasing to decreasing or decreasing to increasing, but they don't occur at some nice rounded curve, right? So some examples of curves that would be smooth or not smooth are the following. Let me get rid of this graph here, this page. So for example, this first drawing, rounded curve, nice and smooth flow here, no sharp corners. This is smooth. That is a smooth graph. Whereas a graph like this, like maybe remember the absolute value function was like a V-shaped graph. See, there's this sharp corner in the graph, a sharp turn. So a graph like this, even though it's continuous, it's not smooth. Right? So being continuous doesn't mean that you're smooth. Right? Both of these curves are continuous. I drew them without lifting my pencil. Right? There's no breaks or holes in them. But one is smooth and one is not. Right? One has sharp corners, not smooth. All right, and then the big notes that are made from this part of the section then, which I'll go back to my first example page. So the big notes to make here are the following. Number one, graphs of polynomial functions, right? This whole section 5.2 from this text, we've been talking about polynomial functions. Graphs of polynomial functions are both continuous and smooth. All right. Polynomial functions graphs are graphs that are both continuous and smooth. All right, so you can draw it from left to right on the XY plane without lifting your pencil. All right, so say going from down here to up there, or up here to, and there's no sharp corners, right? So something like this, where you're going that way forever, right? You draw from left to right without lifting your pencil, so it's continuous. And the turning points, right, the turning points here and here are at rounded corners. They're not at sharp corners, right? So it's also smooth. So a graph like this would be the graph of a polynomial function, right? A graph like this, just a simple parabola, right? That's you draw from left to right without lifting your pencil. There's no breaks or holes. It's continuous. And the turning points are at rounded curves. They're not at sharp corners, so it's smooth as well. So these would be examples of graphs of polynomial functions. And every graph of a polynomial function will be both continuous and smooth. All right, and then one other thing to point out that's really important here is that a polynomial, again, I'm talking about more about polynomial functions in this section. So again, a polynomial function of degree n, so hopefully you recall how to state the degree of a polynomial, of degree n will have at most, okay, now at most means, this many or fewer, will have at most n x-intercepts and at most n minus 1 turning points. And you probably have noticed this throughout previous videos. A degree 3 polynomial will have at most 3 x-intercepts. It can have 1 x-intercept, 2, or 3, but no more than 3. And a degree 3 polynomial can have at most 2 turning points, right? 3 minus 1. It can have no turning points, 1 turning point, or 2 turning points. Well, actually, it's going to have just 2. It can't have 1 turning point. It would have to have 2. But it can have no more than 2 turning points, a degree 3 polynomial. Right? But this is huge, and this is what we're going to be, this concept here, and the fact that graphs of polynomial functions are continuous and smooth will be used in this video, and I think in one future video in section 5.3. Alright, so the first example I want to do is try it problem number 7 from the text. So let's look at that. So there's example 10. Here's try it problem number 7. And they ask us to, without graphing the function, determine the maximum number of x-intercepts and turning points this function could have. All right, and then I'll actually show you the graph. I'll go to that Desmos website, that free online graphing calculator, and then we'll take a look. But let me write this out. Alright, so I've written the polynomial they gave us out. There are 5 terms, 108 minus 13x to the 9th minus 8x to the 4th plus 14x to the 12th plus 2x cubed. Now this is not in the general form, right? Not in descending order. But you can very easily tell what the lead term is, right? It's the highest powered term, the one with x to the 12th on it. Right, the leading term, or the lead term, is this positive 14 x to the 12th. And if you know the lead term, remember you can state the end behavior and all that. It's got an even degree, positive lead coefficient, so it should be going up on both ends, right? As you go to the right, it goes up, and as you go to the far left, it goes up. It should be going up on both ends when we're done graphing this. But it is degree 12. Right? It is degree 12. And according to the statement I made down here, means the graph of this, the graph will have at most, right, can't have any more than this. It can have less than it, but no more than it. Right, the graph will have at most 12 x-intercepts and at most 11 turning points. And that's all they wanted, right? They said, hey, here's a polynomial function. If you know the degree, you can say, the maximum number of x-intercepts the function will have. You can also say the maximum number of turning points the function will have, which will be here 12 and 11. Now, what I'm going to do is go to that Desmos site and enter this. Right, Desmos.com, free online graphing calculator. That's from the last video, sorry. And I'll enter this function, right? We had y equals, or f of x equals, 108. I'll just put it in as they gave it to me. Minus 13x to the 9th. Minus 8x to the 4th. Plus 14x to the 12th. And then plus 2x cubed. All right. Now, Don't know how much we're going to see here. Probably, that's probably why they don't want us to. Yeah, here we go. There's part of the graph up here. Wow. All right. So if I zoom in down here. All right. So look at this, right? Up to the left, up to the right, right? I talked about the end behavior, and it looks like there's one, maybe another turning point in here, and another one down here. It looks like there are maybe 3 turning points, 5 turning points. You know, there might be a one on top of here. You know, if I zoom in a little closer. Yeah, maybe 1, 2, 3. So looks like there are about 5 turning points and no x-intercepts. All right, this graph does not touch the x-axis. The x-axis way down here. All right, so this function has 5 turning points, no x-intercepts. So that's definitely not more than 12 and 11, right? No x-intercepts is not more than 12, and 5 turning points is not more than 11, right? All we're doing here is stating the maximum number that a polynomial function of a certain degree could possibly have, right? And that is all, right? This is all we're asked to do for that exercise. All right. So next example, I want to do try it problem number 8 from the text. So going back to the text, scrolling down a bit, see try it number 8. Now this time we're given the graph of a polynomial function, and again you can tell it's a graph of a polynomial function because it's continuous from the far left to the far right, you know, arrows on the ends. From the left to right, I draw it without lifting my pencil. There's no breaks, there's no holes. And it's smooth, right? The turning points are at these rounded corners, right? They aren't at sharp corners. So you can be given the graph of a function and say if it could be the graph of a polynomial function or not, right? If it's a graph of, if it's continuous and smooth, it might be the graph of a polynomial function. Okay. Now, the question here is, what can we conclude about the polynomial represented by the graph shown in figure 14 based on its intercepts and turning points? All right, so I'm going to draw a rough sketch of this on my paper. Okay, so here's a very rough sketch of that graph they gave us. Now I'm noticing it has 3 x-intercepts. And it also has these 2 turning points, right, where it goes from decreasing to increasing or increasing to decreasing. And so based on this information, I'd say that this polynomial could be degree 3 or higher. All right, now it's probably just a degree 3, but this polynomial function is of degree 3 or higher. All right, because remember, if it's degree 3, it can't have more than 3 x-intercepts and 2 turning points like this has, right? But it can't have more than that. And if it were degree 5, you know, it can't have more than 5 x-intercepts, which it doesn't. Can't have more than 4 turning points, which it doesn't, right? So this could be a degree 3 or any degree higher. But it would also have to have an odd degree as well, because of the end behavior, right? If the ends are going in opposite directions, it's got to be an odd degree polynomial. So it's going to be either degree 3, it could be a degree 3, a degree 5, degree 7, degree 9, and so on. But degree 3 or higher based on the number of x-intercepts and turning points it has. Okay. And that's all. That's a pretty simple one in my opinion, that kind of a question. Alright, so my next example. Now I'm going to be getting into the exercises at the end of the section. So I want to do exercise 32 from the text. So scrolling down here to the exercises. Now these are graphs, and in these graphs they say, again, just like the previous example, determine the least possible degree of the polynomial function shown, right? So they're telling you it's a polynomial function. So these graphs should be continuous and smooth. Alright, so look at number 32 here. That's the one I want to do. Again, I'll just draw a very, very rough sketch of this on paper. I'll just do it here. I won't pause it. I'll just do it here. So again, here's an x-axis, y-axis, and then it looks like this. Like a parabola opening down. So you see there are two x-intercepts. And there's one turning point. Alright, so the smallest degree this polynomial could be is 2. Right? A degree 2 polynomial has at most 2 x-intercepts and at most one turning point. Right. So this polynomial function, I'll just say polynomial, has degree 2 or greater. Because it could be a degree 4 or 6 or 8. It would have to be even because the ends go in the same direction. Right? If the ends go in the same direction, it's going to be an even degree polynomial. But the smallest degree possible is degree 2. And that's all they wanted from us. Right? That's the minimal degree. Degree 2, or greater. That's it, based on the number of x-intercepts and turning points we notice. Great, and I think it's like that for the next several examples I got for you. The next one, I want to do exercise 34 from the text, scrolling down. So this is just a line. So remember, linear functions are degree 1. So I could say this is degree 1 or greater. Right. And if you look at it, right, again, I'll just draw a very rough sketch. Here's the xy axis, xy plane. Line was doing this. So there's one x-intercept, one x-intercept, and notice there are no turning points. It's always going down as you move to the right. There's never an increase to decrease or a decrease to increase. 0 turning points. Right, so based on this information, this polynomial function, or I'll just say the polynomial, has degree 1 or greater. I mean, it could be another degree, a weird looking degree 3, a weird looking degree 5, but it looks like a degree 1. Right, the minimal degree is degree 1. Right. Great. Alright, next example. I think it's the same kind of exercise. I think it's the way it is for most of the rest of this. We'll see. So exercise 36. So yeah, it's the same stuff. Alright, so again, I'll draw a very rough sketch of what I'm saying here. Back on paper. So xy plane. We had this curve. It didn't come down to the x-axis. Came back up. Came back down, hit the x-axis here, and then came back up, hit the x-axis there. And the ends, both ends are going in the same direction, so this has got to be some even degree. Now notice there are, 2 x-intercepts. But there are 1, 2, 3 turning points. And what you're going to be using is like the higher of the 2 numbers that you're finding to help you determine what the minimal degree is. Because if you said, oh, this could be a degree 2. No, it can't. because a degree 2 can't have more than one turning point. This has 3 turning points, so it can't be a degree 2. I would say use the higher number. If it has 3 turning points, the smallest degree it could be is degree 4. Alright, that means this is a degree 4 or higher, or greater. Alright, but that's the minimal degree. Alright, remember, a degree 4 can have up to 4 x-intercepts. This has 2 of them, and that's fine. Right? Has up to 4 x-intercepts. So degree 4 or higher for this one. Wonderful. Exercise 38. I think it's the same kind of problem. Degree 2 or higher. Right, I mean, I'll draw it. Very rough sketch of it. So xy plane. This is just some parabola-looking shape that doesn't touch the x-axis at all. Right, it's all above the x-axis. So 0 x-intercepts. I'll just put 0 x-ints right now. And 1 turning point. And again, I just use the higher number to help you determine. Now, if it has 1 turning point, it means it's got to be at least a degree 2. Right. This is degree 2 or higher. And it would be an even degree, right, because the ends are going in the same direction. So it's degree 2 or 4 or 6 or 8, but you know, the minimal degree that they're asking for is 2. Right? And a degree 2 can have up to 2 x-intercepts. This has 0 x-intercepts, which is, 2 or less. That's fine. Okay, the next example I want to do is exercise 39 from the text. Right? And this is one of the odd ones. So now the instructions are a little different. It says, for the following exercises, determine whether the graph of the function provided is a graph of a polynomial function. If so, determine the number of turning points and the least possible degree for the function. Alright. So 39, again, I'll draw a rough sketch of this. Alright. It's doing this. So, going from left to right. Now, remember, polynomials, mention one more thing about the end behavior of polynomials that I didn't point out in the beginning of this, but you should have noticed this by now. The end behavior of polynomials. They, approach infinity. F of x, the output approaches infinity, or f of x approaches in negative infinity on either end, on the ends. So you're never going to see a horizontal asymptote. Right? All this means is that there are no asymptotes for polynomials. You may have seen the word asymptote before, but that just means there's no asymptotes. The graph's going up forever or down forever on one end or the other. It's not approaching some horizontal line or some specific value. So I'm saying here it's continuous. Right, continuous. It's smooth, right? The turning points, there are 2 of them. I know it's kind of faint here, but this is increasing, then decreasing, then increasing again, right? So we got 2 turning points, but those turning points are at very rounded corners. They're not at sharp turns. So it's continuous and smooth, and also you have no asymptotes. The graph's going to infinity or negative infinity on either end. So this is a polynomial function. This must be the graph of a polynomial function. Right. And as I said, there are 2 turning points. There's only 1 x-intercept. So this is at least degree 3. Right, this is at least degree 3. because of the two turning points, right? A degree 3 polynomial will have at most 2 turning points and have at most 3 x-intercepts. You know, there's only one here, that's okay. All right. So I think the next exercise is the same. You know, exercise 40. All right. So again, nice. I'll draw this up. Now, remember the thing I said about no asymptotes. You know, this look. Now you could argue both ways. You could argue that this is going up forever, but very slowly. But I would say, looking at this, that this is approaching the x-axis. So again, I'll draw my own version of this. So here's the x-axis, right? Now, what it looks like to me is this. It looks like we have a horizontal asymptote at the x-axis. The graph is approaching that, not infinity or negative infinity. So it looks like we have a horizontal asymptote, and based on that, I would say that this is not a polynomial function. It's continuous, it's smooth, but I said earlier, right, if it's continuous and smooth, it may be a polynomial function. Right? There are other functions out there that have continuous and smooth graphs, like exponential functions. Or if you get into trigonometry class, there's sine and cosine functions that have smooth, continuous curves, but they're not polynomials. So because of this whole graph approaching 0 instead of approaching infinity or negative infinity, see over here, I'll say f of x approaches 0, y equals 0. Because of that, I would say this is not a polynomial function. Now, if you wanted to argue that it was going up to infinity, if it looks like, it looks like it's curling up. If you want to argue that, fine, but as long as you make the point to say that, right? Say there's no horizontal asymptote, the graph is approaching infinity or negative infinity on either side. If you want to make that argument, fine. But again, to me, it looks like there's a horizontal asymptote here, and polynomial functions do not have a horizontal asymptote. All right, and since it's not a polynomial function, I'm not going to talk about degrees at all, right? So I'm just going to move on. All right, and this is my last page. I got just 2 more exercises I want to do from the text. Exercise 42. All right, so remember what I said about no asymptotes. This has vertical asymptotes. All right. So there's this like vertical line here, vertical line here. Now, it's doing this, but it doesn't go beyond these walls. It's not going to the right forever, to the left forever. It's going up forever and down forever, sure, but just between these, right? So again, there are some asymptotes here. Right, there are some vertical asymptotes. And because of that, this is again not a polynomial function. All right, polynomial functions go to the left forever and to the right forever. Without lifting your pencil, and smooth, and they either go to infinity or negative infinity, go up forever or down forever. But this is stopped. You can't go there. There's no graph beyond this dotted line over here. There's no graph beyond the dotted line over here. That's not going to happen in a polynomial function. So again, not a polynomial function. And if it's not a polynomial function, we can't talk about degree. Right, there's no degree to it if it's not a polynomial. All right, and then my final example, exercise 44. That's 43. Okay, this is a very simple one. This I actually drew a picture like this earlier. When talking about smooth functions and not smooth functions, this one looks like this. And then very sharp corner. All right. You see this sharp corner right here. Right. meaning the graph is not smooth. And if it's not smooth, then it can't be the graph of a polynomial function. Now that might be an absolute value function, right? You've seen absolute value functions before. But it's not the graph of a polynomial function. Okay, so once again, just kind of recap everything. The graph of a polynomial function will be continuous, smooth, and have no asymptotes, right? The graph will be going to the right forever, to the left forever, and then, going either to infinity or negative infinity, going up or down forever on either end. Right. So keep all that stuff in mind, and hopefully, watching me go over these examples here help you in some way when you're asked to, see if a graph or identify if a graph is the graph of a polynomial function or not. All right, and thank you very much for watching.